let's use the central limit theorem then to talk about some categorical data and to get some inference. Okay, so here are the example. 2 years ago, Stats Canada reported that 13% of Canadians use cell phones and no longer had any sort of landline. Okay, so here the question is, do you have a landline or do you just use a cell phone? You say just cell phone or landline and cell phone. Okay, so here this is categorical data. Here the sample size, we're going to talk to 500 people because n is more than 1, and especially because the number of successes here will be more than 10 and the number of failures will be more than 10. Here we should use the central limit theorem. Anytime you've got the sample size being larger than 1, then you can use central limit theorem. Okay, so what is the probability that more than 15% of households now will say they don't have a landline? Okay, so here originally we believe that the proportion is based on what we knew from Stats Canada, okay, which is the middle should be 13% or 0.13. We're talking about here a different proportion, a proportion of 15. Okay, so we're going to convert this 15 into a z-score. So here's how I can do that. Of course, the middle is just going to be converted into a 0 for a z-score. Here, this value, this p hat value of 0.15, subtract the middle and divide by the standard deviation, which here p is 0.13. So here the standard deviation is going to be 0.13 times 1 minus 0.13 divided by n, which here is 500, and then I'll take the square root. This denominator is the standard deviation of the sampling distribution for categoric variables. Okay, so I can convert this into a z-score. Okay, I find this value, I can convert it into a z-score. Here then I can look it up using the z-table. This is 1.3 as a row, match it up with 0.03 as a column, and I find this area to be 91-ish%. Okay, so when I'm looking at my picture, of course I know that the z-table gives me the cumulative area, or because the picture looks the way it does, it's clear to me that this side, the left side, is the 91%. The right side then, this is the probability we're looking for. This is more than 15%, then would be 1 minus that. So I can do that. 1 minus 91% is obviously somewhere around 1%. So this area is about 9%. Did I say 1%? I meant 9%. Okay, you can also use the computer to do this very similarly. Okay, so here probability distribution normal. I can use cumulative. If I'm using z-scores, the middle is 0 and the spread is 1, and I found the z-score to be 1.33. Again, something close to 91%. Okay, you can also use things as they are. The middle is not actually 0, the z-score is. The middle is actually 0.13. Okay, so I can redo this yet another way. Say the cumulative distribution of the normal. Here the middle is actually 0.13, and the value I'm looking for is actually 0.15. However, the standard deviation, okay, the standard deviation is the denominator of this formula here. It's not just sigma, it's not just p, it is p times 1 minus p divided by n all square rooted. So you'll have to find that calculation. Maybe you're just better off just solving to get a z-score, seeing as you have to do half of this step anyways. But if you don't want to do that, here's the standard deviation, here's the denominator, the standard error, or the standard deviation it's called, 0.04756. Okay, so I can do that by putting in here the standard deviation 0.04796. I just want to make sure. 0.04756. This is a 5. And this is a 6. Okay. So here I've got the standard deviation. When I press OK, I expect a number very similar to this number. And I didn't get that. What happened here? Let me just check to make sure my calculations are correct. Okay, so 0.13 times by 1 minus 0.13, divide by 500, and I'll take the square root of that, oops, I don't know what I was calculating, but the standard error is the thing that's off. This is why you may be better off just using the z-scores. Okay, actually when I recalculate the standard error, what I actually get is this value. I must have a little typo in my notes. Now you can see here I get a value much more similar to what I expect, with of course some rounding issues. Okay, so here 91% any which way. Now I want to explain something. Here B is asking for us to use this information to make some decisions. Okay, so it says suppose the sample proportion computed from the 500 tries does in fact turn out to be 15%, like we've calculated here. Does this indicate the percentage of households do not currently have a landline has increased since 2013? Okay, so what I want to emphasize here is that there are two possibilities of things going on here. Okay, so what has happened is that here we believe that the percentage of people who only have landlines is 13%. When we took a sample, we found that our sample was 15%. Okay, so the question here is this 15% actually pretty close to 13%? The question is 13 similar to 15? And it depends, of course. It always depends. I mean, yes, on one hand, 15 is pretty close to 13. On the other hand, well, it's two numbers away, so maybe not that close. Okay, so there are two possibilities. Either the proportion of people who have only landlines really is 13, just like we thought it was. Then, if that's true, we found this area to be 9%. So if that's true, then we have a 9% chance of getting a sample where we actually found that the sample had 15% or more. So what this would mean is the fact that we got a 15% instead of a 13% like we expected, the reason that we got that is just due to chance. Okay, so the probability of this happening is 9%. Okay, the other possibility is that this 13 is actually old data, okay, and things change. Maybe the reason that 15, we got a 15 instead of a 13 is because the proportion of people who have landlines has actually changed, and it is now more likely to be closer to 15 than it is to be closer to 13. Okay, so that's the other chance. That's the other possibility. So which one is more likely? Well, we look at this number, we found this area to be 9%, and the question is 9% high? Do you believe that there is a chance, do you believe that a 9% chance of getting a 15 when you expected a 13, do you believe that 9% is high or low? If you're saying that 9% is high, then it is likely that the percentage has not changed. The proportion of people that have landlines is the same. If you think 9% is kind of low, then what you're suggesting is that maybe the middle really wasn't 13 like we first supposed it was. I know that this is a difficult concept to understand, but really we're trying to use the information to tell a story. Okay, and of course the story is not 100% this or that. We're trying to use the probability here, the area, to start telling us about this. So I want you to review this idea a few times until it kind of makes sense.